by two other study cases in order to discover the inner part of the globe. It's the same process than for ultrasound. When a doctor wants to see maybe an embryo or a baby or any organ in the body, he uses ultrasound. The ultrasound waves circulate into the body, and they encounter different layers, different tissues, organs, and these waves are reflected or refracted, and we can have an image, a picture of an organ inside the body. You understand that? And with seismogram, we can do the same job in order to discover the structure of our planet. Okay. First of all, I just wanted, it's the first page, the paragraph number 4 of our paper, was to show you the behavior of the different waves. Like you can see on the scheme, maybe I can open it. So it is here. Well, now I think you can see the document.
Oui, on peut le voir.
Okay.
Yes.
You can see donc when an earthquake occurs, different waves start from this point called the focus or the hypocenter. We have direct waves which arrive directly to the station, but for the volume wave which circulate into the globe, they will find on their trajectory, on their path, maybe here what the teacher which teach physics call a diopter, a diopter. That means the wave encounter a green rock here, which have a different characteristic than the gray one here. So the wave, it depends with the angle she touch the green rock, but this wave can be reflected. She bounces on this layer, which is called, we will call a discontinuity, or sometimes the wave will be refracted. It will circulate inside the green layer, and then she will go to the station. Okay, so a wave can have different destiny. Okay, and if we study the different ways which arrive at the receptor, we can imagine a speed, a path she has had. Okay? And sometimes we will see an example in a few minutes where a wave doesn't appear here. She's not, it's not arriving. He's lost inside the earth. So we will see this, and we will have a conclusion about this fact. Is it okay for you, for the different behavior of the waves? So they inform us about the layer, the rock which are crossed. Okay. Well, this is the first thing, and the second thing, what a small reminder from Jean-Luc session on Tuesday, 4 days ago. You remember, we can calculate the speed of a wave using, of course, a distance and a time, the travel time. This is something which is very important for us to understand and to work in seismology. Okay, so I remind you the different ways to know the speed of a wave. I would like with you to take an example. It's the Greek earthquake which occurred last Tuesday evening, the day last Tuesday. I can open it. So I stop the page and I open it. I come to EduMed. So as usual, you remember, I'm going in the data center in Seismo. I choose seismogram interesting for us. I choose the UK version. I click on English. And the first one here, it's the earthquake magnitude 5, which occur in Aegean Sea in Greece, 29 November, 4 days ago. I open it with Spectroglobe 3D. Okay, donc you remember I can double click on X station to have the position of the hypocenter, of the epicenter. Okay. Second one. So I have now 2 points, and I will take also a point, a town in Turkey. Okay, donc c'est ici. Okay, so I can see the epicenter of this event is here. So we have different solutions to evaluate the speed of a wave. Usually we take the first wave which arrived, called P wave. You remember we have some details here. The epicentral distance is 185 kilometers, 242, etc. So we can have some details for the distance. You can use too this small image here. It will give the metadonnées, the metadata associated to the seismogram. If I click on it for KLV, The metadata gives us the date, 29 November, etc. They give us, the metadata give us the original time, 20 p.m., universal time, GMT time, 26 minutes, 39 seconds. So we have details on the event, the magnitude also too. Okay. We have, you remember, we can have two, the TO event. Yeah. So it's indicated, and we have some the arrival time of, for example, the P waves here, which is 29.6 seconds, for example. Okay, we can use to, you remember, the autochron down on the left here. And for example, if I have an arrival time which is 29 or 30 seconds for the P wave, 30 seconds, donc I have to take the short distance scale, and TP minus TO, 30 seconds, means 200 kilometers, 212, okay? The data which is written here, it's 185. You remember the discussion we had with the model which is used to calculate, in theory, the arrival times, okay? So we have approximately 200 or 185 kilometers. Okay, so you have a lot of helps for you or your students to calculate the speed of the wave. Is it okay for you? No question? Okay.
No question, no question. Go ahead.
Okay, thank you, Jean-Luc. So we wanted now to consider a first study case. It's it concerns the event which took place in Josier in 2014. So I come back. Base de données Seismo. I take the seismograms for educational purpose. I'm still in English, and I'm looking for the only earthquake which occurred in 2014. Josier, it's near the Italian border, au niveau de Barcelonnette, like this, just on the other side of the Alps from Cuneo. And I display with Tectoglobe 3D. Okay, now you are very, it's easy for you to understand what we are doing. We have the different stations which recorded this event. As usually, you can, if you want, with your students, if it's your purpose, your work prepared with the students, you can open the different stations, to locate the epicenter. So from Nice, we have the red circle. From Corte in Corsica, okay, we have a second circle. CFF, we have a third circle. We can take Annecy too if you want. And we can surely locate the epicenter, which is here. The program gives us the depth of this event. Just like for the earthquake in La Spezia we were studying with Jean-Luc. You remember it was 8 kilometers depth. This one is a very superficial event, only 3 kilometers under the surface. So I can, and you can see on the paper, you can in action add an object, and this object will be an underground landmark. Okay, this landmark is not 200 kilometers, but just 3. And then it's written in French, but ce modèle permet you double click on the globe at the level of approximately take place the epicenter, so it's here. Okay, so I have a small star here, and when I will draw a cut on the map, I will have the hypocenter which will be placed at 3 kilometers depth. Okay, we can see it in few moments. So what is interesting in this case? We have 2 stations, CFF in center of France, probably Clermont-Ferrand, maybe, and Corte in Corsica, which looks at the same distance from the epicenter. If I see on the seismogram for Corte and CFF, effectively we have the same epicentral distance. Okay, so I would like to give you a small job. Could you tell me when you display the original time event? Could you tell me when the first wave arrived in Corte and in CFF? Can you note it? And can you please, so you see, you can open the seismogram and I give you this small job to note the arrival time and to calculate the speed. Okay? Okay, I give you 30 seconds. Go. Alors. Is it okay for everybody?
So we have the same distance, and
Yes.
we have to mention the time. I mean, to calculate the time here.
Yes, okay. So calculate the time for Corte, for example, for the first wave on the seismogram.
It says 46. How much?
46. That 2 or 3. It's okay. For Corte, maybe 2 or 3.
Okay.
6.8 kilometers second. Maybe
6.8. Okay. 6.8. Donc 46.2, and for CFF, the first manifestation of the wave here, it's about alors combien? 46 maybe, 47. Are you okay? 47 seconds.
6.6 kilometers per second.
6.6. So, is everybody okay with that? So
Yes.
we have the same distance. So we can imagine the waves arrive at the same moment. But we have a delay. The P wave which arrive in CFF arrive approximately 1 second later. Is it okay for you? 1 second later than in Corte. The speed, okay, so we have here, we encounter what we call a scientific problem. We imagine the arrival time will be the same, but it's not the case. Why? So with the students, we can have a discussion. Do we have any hypothesis to try to explain this problem? The waves which go to CFF have a travel time about 1 second more than the waves that go to Corte. Do you have any hypothesis?
The different kinds of rocks.
of rocks, yes.
Okay, different kinds of rocks. The students can see that here we have the Mediterranean Sea. Here we have just continental rocks. Okay. So maybe the problem is due with the rocks on the travel of these waves. Okay. When I see, I can have, when you go to the seismograms, yeah, Is it okay? You can have
Aspetta, come?
a
Là è comodo perché c'è il semaforo. Siamo sicuri che aspetta.
Qualcuno ha l'audio acceso?
yeah. Is there any question? C'est bon? It's okay. So
C'est bon,
I
c'est
can-
bon, tu peux
I
continuer.
can have a projection of the stations on a globe section. Oh, look at this. I have the Earth, and here on the top, we have all the stations in southeast of France. And you can see they are very near the hypocenter. We just are here in the waves do not travel inside the Earth, but they stay on the surface. Here are the 5 or 6 stations. Okay, so we can understand that the waves to CFF or to Corte stay at the surface of the Earth. Okay, they are very superficial. Okay, and I can precise this. I come back. Alors, pourquoi j'ai plus... Okay, I come back to the car. Okay. And I can draw a cross section in this sector. Okay, so actions, draw a cross section. I have the menu here. I click on 2 points on the card. So I want a cross section between CFF and Corsica. I can have it on the right hand side. First of all, I can find the hypocenter situated at 3 kilometers depth. Okay. I can have the topography between Clermont-Ferrand, center of France, and Corte. I have the Ligurian Sea, the Mediterranean Sea here, and okay. And if I draw, I can display a geological data, which is the discontinuity called Moro, for Mohorovicic, the guy who discovered this discontinuity. So I put the Moro, and as you can see, here is the Moro line. It's a discontinuity at the basis of the crust, the layer, the globes, the Earth's layer called the crust. And you can see that when a wave leaves the hypocenter to go to CFF, it will stay inside the crust, as well as to go to Corsica, it will stay in the pink layer called the crust. But we have two different crusts because one is under the sea. So we probably have a difference between a continental crust and is it maybe an oceanic crust? This will explain the different travel time between CFF and Corte. Okay? And now I can try to see if what I say, what I imagine is right. So I will use the KMZ file, which is open with Google Earth. But it can be open too with Spectroglobe. So in file, alors c'est dans le file, hein, I can import different, I can import an image or a CSV, it's like an Excel file, and I can open a KMZ Google Earth file, KMZ. So I'm going to search it in my computer. In my computer, look on my computer, it was put in my documents, EduMed, Cuneo, Visio, November. So the file is here. I click on it to open it. And he has metadata, meta characteristic with the position, latitude, longitude, and it comes just at the right place between Sardinia, Corsica, and France. Okay? Can you open it on your computer too?
Yes,
Or do you have any problems?
no problem.
Okay.
It seems no problem, yes.
Bon, right. Carla, is it okay for you?
Just a moment, because I use the iPad and
Ah oui.
I
Okay.
need some more time.
Ah, yeah.
Yes, no problem, no problem. No problem. So it's not very okay. And what can we see? We can have the rock in the ocean deep. We have volcanism, volcanic rocks, probably basaltic rocks. We have a kind of symmetry on both sides. We can imagine we have a kind of rift here and a symmetry between this axis. We see we have some faults on the French or Italian Riviera. Also on the western part of Corsica. So we can imagine we have here a zone which were open, which opened the Ligurian Sea. Now this rift is dead. It doesn't go anymore. It's blocked. The axis of Corsica and Sardinia is blocked in this position. But we do have in this place a true oceanic crust. We can see here also, we can see that the moho, it's more superficial than here. Here it's about 20 kilometers, 30 kilometers, and here the moho is 18 kilometers. Okay, so we do have an oceanic crust here and a continental one here. Maybe it's not very important in the curriculum in Italy or in Greece or in England. I don't know, but maybe it's important to know the structure of the crust, the structure of the superficial part of the earth for you. Okay, and there is a last argument, and to see to have a proof of the difference of the two crusts. It's the statistic distribution of the. Alors, je vais come back. So, of the altitude.
Il faut que tu désactives ta cross-section.
C'est ça.
Il faut que tu ailles à Action et tu désactives cross-section.
Action, c'est ça. Donc, cross-section. OK. Je reviens dans Action, Elevation Distribution. OK. So I have the profile from CFF to Corte, and we have the frequency of each elevation. We have, you can see here, I have something which is 2 kilometers high. Okay, that means 15% on this cross section, on this travel. We can find 15% time an elevation of 2 kilometers, between 1 and 2 kilometers. Most of time we have an elevation between 0 and 1 kilometer. But sometimes we have another boss, je sais plus comment on dit, another high. We have two kind of, like the back of a camel, up. And here we have the elevation, which is negative because we are inside the sea, and that gives us the information that we have two geological entities, two different entities. One oceanic and one continental. Okay, so in this example, we have seen all the arguments seismology gives us to have a well knowledge of the crusts, and we can compare oceanic and continental crust. And as a conclusion, okay, inside the crust, the speed of P waves is about 6 or 7 kilometers, no more. But the P waves travel faster in oceanic crust than in continental crust. Okay? And of course, according to your curriculum, you can use the studying of the rocks with a microscope or different cards to study the different crust of the world. Okay, and there is no question, we can see now another example, but we will go deeper in the planet, in the globe. So I propose you to open another event which is the one is Peru, Ecuador in 2019. Peru, Ecuador. I display this event. What can we see? We have now stations which are displayed all over the world, not only in the suburb of Cuneo or in the southeast of France. Now we have an earthquake, very powerful, and the waves had enough energy to travel all over the world. We can, if we want, we can have, for the third time, we can locate the event. Okay, it's here at the border between Peru and Ecuador. Okay, and we can display these stations on a globe cross. And do you see the difference with the other event? We have stations, the one in America, this one probably, or this one, I don't know. One in the Caribbean Sea, another in different place, and even in Coco Island, quite at the opposite of the hypocenter. That means the waves which leave the epicenter can go at 30 degrees. You can see an angle here with the center of the Earth. The CALF, C-A-L-F, is about at 90 degrees angle, with the center of the globe, and COM, K-O-M, or Coco Island are quite at the opposite. So they travel all the world. So now we will have a kind of ultrasound, not with our body, but with the planet. Okay, so we can work. We can work on with the table which is presented on the document. Donc là, je vais faire un nouveau partage. Voilà, il faut que je ferme d'abord. Nouveau partage. Voilà, voilà. Okay. And okay, if you want a little work again, if you want, can you calculate? Can you first of all note the length of the seismic ray, the seismic line which arrive is RPN, ANMO, you note the distance. So maybe the girls can do this work, and the men, Otis, and maybe other, you can note the length for Kunk, Com, and you calculate the speed. Okay, I give you a few seconds for that. For example, for ANMO, I have a distance which is about 5,240 kilometers and a travel time of 492. That means I can calculate a speed which is about 10.6.
10.5.
5, okay. And for RPN, somebody have the speed? No, I have not, but it's probably 10, maybe. Kunk. Is somebody have the speed? No, I have calculated about 10.5, something like that. So what can we see? We can see that when the waves circulate for a long distance, that means they are circulate deeper in the globe, in the mantle. The speed is increasing. 9, 10, 11, 12. Okay? The speed is increasing. But you can see here that, okay, they are circulating deeper and deeper, but they stay in the mantle here. And we can have P waves. But when the waves encounter an obstacle here, you understand, it's the core. They are déviés they are deflected, and we can find them not in this shadow zone here, where we have no direct waves, but we have waves which has been deflected, reflected, and we find them again for distances up to 140 degrees. Okay, and here we have no direct waves. You can see the travel of these waves. If they travel inside the mantle, they are called P. Okay. If they travel inside the core, or the kern in German language, kern is the nucleus, the core, we spell them, we give them the name of K, and if they circulate inside the inner core, we call them E. So we have in Kunc waves which are called PKP, okay, P, K, they circulate inside the external core, and again in P. But for COM here, they circulate inside the mantle, P, inside the external core, K, in the inner core, and we encounter them again as K and P. So we call them PKI, KP. Okay? And we see that these waves which have circulated in the core are brutally slowed down in contact with the core. We just find here speed with 10 kilometers per second. Okay, so if I come back to the tectoglobe, I have here the velocity model, okay, down in the middle, velocity model, which is precise, a preliminary reference Earth model. We can see that for the P waves in red, the velocity increase from 6, 7 in the crust, and then deeper in the mantle, they go from 8 to 12, 13, 14. Brutally, they are slowed down at the contact with entering the core, and then it's increasing again. Second conclusion, you can see the S waves doesn't appear here. That means these special waves has encountered a liquid, and we can have the conclusion that the external core is liquid. Okay, the outer core is liquid. So we can have a lot of precision about the interior of the globe, and we can also have details about the size of the core. When a station was put on the Mars planet, it was to study the inner part of the planet, and we can have on Mars, just like on the Earth, details on the is there a core? What is the size of this core, etc., etc. So we wanted with these two study cases to inform you on the way to know what do we have under our feet and very, very deeply. Okay? Okay.